So, welcome to lesson 3.4, which is all about nonlinear dynamics. Now, with linear dynamics, we're talking about systems in which in the equations describing the system, the variables are not raised to anything more than the power of 1. So there are no squares or cubes or anything like that. And in such a situation, the dynamics of the system are very simple and straightforward. So it just means that the output of the system is directly proportional to the input. So if you double the input, you double the output. If you halve the input, you halve the output. Very straightforward and simple. But with nonlinear systems, we can have squares, we can have cubes, we can have two variables multiplied together, we can have sines and cosines, we can have all sorts of things. And in such a situation, we can get much richer and more complex dynamics. And we've seen some of those in the lesson on calculus. So we can have things that show explosive growth, shooting off like a hyperbola. Or we can have negative feedback so that the system evolves towards some limiting value. Or we can have oscillations, or we can have chaos. So there's a much richer range of behaviors that we can get with nonlinear dynamics, and we expect to see those kinds of rich behaviors in social and historical systems. So that is why we're studying nonlinear dynamics. Now, with nonlinear systems, though, the problem is that the equations can be too complicated to be solved. Or if it is possible to solve them, the solutions can look so complicated that it's difficult to get a feel for what they're telling you, for what's going on. So for that reason, people tend to study nonlinear systems through their phase portraits of their phase space. So we'll start off by looking at phase space, what it is and what it can tell us. And we're going to take the example of the logistic equation, x dot dx by dt, the rate of change of x with respect to time, equals x into 1 minus x. And we can draw a graph of this. And it looks like this. So we can see that from this equation that firstly x dot is 0 when x is 0, or when x equals 1. That makes that 0. So x dot is 0 at 0 and 1. And the only way for this to be positive is for x to lie between 0 and 1, because if x is less than 0, then x is negative, and 1 minus x will be positive. So it's a negative times a positive, so it will be negative. So it's always negative below 0. And similarly, if x is greater than 1, that will be positive, but 1 minus a number greater than 1 will be negative. So again, x dot is going to be negative. But between 0 and 1, x dot will be positive. And in fact, it reaches its maximum when x equals 1 minus x, which is at x equals a halfway between. And now we can draw on this graph how the system would be behaving at different points or in different regions of this graph. So let's start when x is negative. Well, when x is negative, we can see that x dot is negative. It's below the axis. So here, the system will be moving in the negative x direction. So if the system has a value x below 0, it will be moving negatively. What about above 0? Well, here x dot is positive. So in this case, the system will be moving in the positive direction. What about here? Well, x dot is still positive, so it'll be moving in the positive direction. And we also see that it's at its maximum value. X dot is very large here, So we can draw a larger arrow, longer arrow, to represent that. And then as we get towards 1 here, still positive, but x dot's decreasing, so x dot will be a bit smaller. So we can have a small arrow there. And then what about on this side of 1? Well, now x dot is negative, so it will be moving in the negative direction. So it'll be moving that way. And then if it's exactly at 0, x dot is 0, so it won't move at all, so it will stay there. And if it's at 1, again, x dot is 0, so it will not move, it will just stay there. So we have 2 points where the system will stay and reside at, and we call those fixed points. And we also see that there's a bit of a difference between these 2 fixed points. So from this fixed point at 0, the system tends to move away from it. So we call this a repelling fixed point. Whereas for this fixed point at x equals 1, the system is moving towards it. If it's below it, it's moving up. If it's above it, it's moving down. So this is an attracting fixed point. And now there are 2 things to note about this. Firstly, that we can tell where the fixed points are because they're just the points where this expression makes x dot equal to 0. When they're multiplied out or put into these brackets like this, it's very straightforward to see. So we can see it's when either x is 0 or 1 minus x is 0. So that tells us that x is 0, and when 1 minus x is 0, that tells us that x equals 1. So we can see from the equation where the fixed points are going to be, and we can tell what kind of fixed points they are from the slope of the graph. So if the slope is positive here, moving up when it goes through the fixed point, then that is a repelling fixed point. And if the slope is negative as it goes through the fixed point, moving downwards, then that will be an attracting fixed point. And we can also have a rather quirky situation like this, where the graph just touches the axis. X dot and x. So it just touches the axis. So this is a fixed point because x dot is 0. And now below the fixed point, x dot is positive, so it will be moving towards it. At this point, x dot is increasing, and above it, x dot is also positive, so it will be still moving in the positive direction. So from below, this looks like an attracting fixed point. From above, it looks like a repelling fixed point. And this is known as a saddle point, after a saddle. So, you know, the shape of a saddle is it curves like that in that dimension and like that in that direction. So that a ball on the saddle would, in this direction, it would be moving towards the middle of the saddle. It would be rolled towards the middle of the saddle. But in that direction, a ball would tend to roll away from the middle of the saddle. So it's like this. From one direction, it moves towards it, and from the other direction, it moves away from it. And now we have here got an x dot axis, but we've also got these arrows. So we don't really need the x dot axis. The arrows themselves tell the story. So we can redraw this like so. So we've got rid of the x dot axis and we're just looking at what's happening along x. So otherwise it's the same thing. We've got these two fixed points and we've got these arrows showing the direction in which the system will move in each region, and similarly over here. So this is a phase portrait, and this is the phase space. Now this is a one-dimensional phase space. This is just a line. And we can see that in this one-dimensional phase space, we can have three types of fixed points. We can have a repelling fixed point, we can have an attracting fixed point, or we can have a saddle point. And there's only three basic types of behavior that we can get. We can either stay at a fixed point, so x dot is 0 here, it won't move, or we can move towards a fixed point, as here, or we can be moving away from a fixed point to infinity, either in that direction or that direction. So those are the only three behaviors. Stay where you are, move towards a fixed point, or move towards plus or minus infinity. We cannot get oscillation with a one-dimensional phase space, because the phase space tells us where the system will move to at each point. So if it's, say, at this point, it's moving in that direction. So it can't be moving in that direction. It's got to be, it can only be, the phase space can only show you moving in one direction. It doesn't change. So the system can't move through it in that direction and that direction. If at this point it's moving in that direction, it will always be moving in that direction. It can't come back again. So you can't have oscillation, something moving back and forth through a point. Now you might say, well, what about x double dot equals minus x? That is the equation of a simple harmonic oscillator. So that gives oscillation, and it's only got one variable, so it looks one-dimensional. But the thing is that with a phase space portrait, we're showing x dot. X dot is what these arrows represent, how x is changing at each point. And so it doesn't show x double dot, but this expression is for x double dot. So what we have to do to cope with that is we firstly define x dot equals v. So that's just saying the rate of change of x is equal to v for the speed. So that's really just a definition of speed. So we define v equals x dot. And then if we differentiate v, we'll get x double dot. So that tells us that v, so v dot, which is the same as x double dot, is equal to minus x. So now we've got equations that just show the first derivative. X dot equals v and v dot equals minus x. But now we've got two equations. So we've got a two-dimensional system. So we're going to have a two-dimensional phase space. So that's what we'll consider next, two-dimensional phase spaces. Now for a two-dimensional phase space, we'll take the example of a system of Lotka-Volterra equations. So we'll have x dot equals x into 1 minus y, and y dot equals y into x minus 1. And as we should recall from the calculus part of this module, this will generate cyclical oscillations. Now, if we wanted to study how x dot and y dot depended on x and y, we would need 4 dimensions. We need the axes for x dot, y dot, x and y, so 4 axes, but we only have 3 dimensions to play with, so that would be rather difficult. So this is where the idea of plotting the phase space in terms of arrows showing the direction of x dot, or in this case now x dot and y dot, comes into its own. So we only need two axes, one for x and one for y. So let's have a look at that. Okay, so this is what the phase space looks like for the Lotka-Volterra equations. So we have two fixed points at 1, 1. So when y equals 1, this is 0. 1 minus y is 0, making the whole thing 0. And when x is 1, this is 0. So at 1, 1, this will be a fixed point. Both x dot and y dot will be 0, so there will be no change. So it will just stay at the xy position it is. And then the other fixed point is at 0, 0. So when x is 0 and y is 0, again, this side is both 0. So it will, if it's at 0, 0, it will just remain there. And then at this point, if it's somewhat away from it, we'll get a cycle around that point. So if we look at, for example, if it's just above 1, if y is just above 1, then this will be negative. So x dot will be negative, so it's moving to the left. And if y is below 1, then y will be less than 1, this will be positive. So x will be moving to the right. And then similarly for y dot, if x is less than 1, so here, then y dot is negative, so it's moving down. And if x is greater than 1, this is positive, so y dot is positive, so it'll be moving up. So we have it, the system will be tending to cycle around this fixed point. And this is known as a centre. So it's a type of fixed point that we didn't get before. It's a new type where there can be oscillations around that fixed point. And then what about the fixed point at 0, 0? Well, if we look here, we can see that the system is moving towards that fixed point from one direction, and it's moving away from it from the other, in the other direction. So this is again a saddle point. So it's like a saddle where from one direction it's moving towards this point, and in the other direction it's sliding away from it. So we've seen two kinds of fixed points that we can get in two-dimensional phase space. So one is which we've just seen, the saddle point, where it's moving towards it along one axis and away from it along the other axis. And we've seen the idea of a centre, so where the arrows point in that direction around it, leading to a cycle. And some other types of fixed point which we haven't got here but we can well imagine could occur is an attracting fixed point, as we had in the one-dimensional case, and a repelling fixed point. Now, although I've drawn these arrows as straight, they don't have to be straight. You know, they could curve in towards that. So we could have something that looks like a spiral, spiraling in to a fixed point. But, you know, it's equivalent. And then there are a couple of other types of fixed point we can have with two-dimensional phase space. Well, one is not a fixed point so much as a fixed line. So it's a whole set of points which could be attracting. So if you're up here, you're attracted to this point. If you're here, you're attracted to this point. If you're here, you're attracted to this point. So there's a whole line of attractors. And then last type that we can have is what's known as a limit cycle. This is where it's like a line of attractors, but they're joined up and it works as a cycle, so that if you're out here, you're attracted in towards this limit cycle. So wherever you are, you're drawn in, and if you're inside it here, you're also drawn out to join up with this limit cycle. Now that is different from what we had here, because here we had many cycles around this point. So this is a center that can have lots of cycles around it. The further away you are from it, the bigger the cycle you're going in. But you know, you can be in that cycle or you can be in that cycle depending on where you are. But with a limit cycle, there's one particular cycle that if you're out here, you're drawn into it and you end up wherever you are going around that particular cycle. So if you're out here, you don't go on this cycle, you'll be drawn in, sucked into this limit cycle. So that's another kind of behavior we can get when we go to a two-dimensional phase space. And the key addition here is the possibility of cycles, oscillations. And as we might expect, if we go to a three-dimensional phase space, we can get other kinds of behavior. So let's just think for a moment about two-dimensional phase space, and imagine the two-dimensional phase space, or sorry, the system with the two-dimensional phase space is confined to some box. It's kept within a certain boundary. Then as the system evolves, it can sort of go around in this box, but eventually it's going to hit its own path. And at that point, it's ever after going to carry on along the same path, because you know, the phase space shows you where you are at a particular point is where you move to next. So if you go through this point again, you will have to carry on following exactly the same path that you followed it from it before. And you know, you can imagine a more convoluted path, but eventually if you're kept inside a box, you will eventually go into a cycle, and then your whole path, you will eventually hit yourself, hit your own path, and then afterwards you'll have to carry on. So ultimately your path becomes predictable. It must be part of a cycle. But that's not the case when we have three dimensions. So let's have a look at that. Okay, so I've drawn here a three-dimensional phase space system, which is confined to a three-dimensional box. So it has to remain within bounds, but it can be looping around on itself. And unlike in the two-dimensional case, where it was when it kind of crosses, it's going to have to join the same path. Here it can miss itself by crossing in the third dimension, being separated in the third dimension. So this has come round and it's going to meet itself, but it's slightly behind, so it's separated, so it doesn't hit itself. And in this way it can keep on going, exploring through the box forever, always using the third dimension to slip past itself, if you like. And so its path becomes rather unpredictable, because it never repeats. And what's more, it can pass very close to where it was before, as here. So at this point it can be extremely close to itself and yet go off on a different path. So unless you're very accurate in telling precisely what the coordinates here are, you can't tell which of these paths it is going to go on. In fact, you never really can tell, because they can get infinitely close and yet still go on different paths, and you cannot be infinitely close in your measurements. So the path remains bounded within a box, but it is completely unpredictable. It exhibits what's known, and we've just mentioned it before, sensitive dependence on initial conditions. So it depends precisely where you are, which path you're going to follow. And two very, very close initial conditions can lead off to completely different trajectories. And this is chaos. So with a three-dimensional phase space, we get a new phenomenon, chaos. And we'll come back to chaos later on in the lesson. Okay, and now I want to talk about the dynamics of a pendulum. So this is a pendulum. It's a rigid pendulum. So it's, you know, not a bob on a string, but it's a pendulum nonetheless, as it can swing around its equilibrium position. And because it's rigid, it can also be at the top of the swing and kind of balance on itself. So this pendulum has two fixed points. It has one when it's hanging vertically down, and it has another when it's just carefully balanced at the top of a swing. But there's a difference between these fixed points, because this one is a repelling fixed point. So if it moves slightly away from it, it keeps moving away. Whereas the fixed point at the bottom is an attracting fixed point. It moves towards it. And the reason we're going to study this is because this system may be an analogy for things that we encounter in history and society. So it may be something like the sizes of empires, or the fraction of the world's population that is living in cities, the world's urbanization fraction. So I said that this pendulum has two fixed points, but in fact it has more than that. So if we say that this is a fixed point when it's vertically down here, and we call that the angle 0, then the next fixed point, which is this unstable or repelling fixed point at the top, is 180 degrees round the circle, so pi radians. And then as we continue round, we've got another fixed point when we're 360 degrees round, 2 pi radians. And then if we keep going, we've got the next repelling fixed point at 3 pi radians, and then another attracting fixed point at 4 pi radians, and so on. Now, you might say, well, you know, you're calling it a different angle, but it's really just the same angle. I mean, it's just still hanging down, which is perhaps true in this case. But if we're the thing that's corresponding to angle in our socio-historical examples is something like the sizes of empires, then the sizes of empires is increasing around here, and this is a larger size of empire. So there is a tangible difference. So it's if it's the urbanization fraction, it's the urbanization fraction increases around. So this next fixed point is a larger urbanization fraction. So it's a different value, definitely a different value to the variable. And we mentioned earlier that when we look at the growth of empires through history, they're like this. It doesn't increase smoothly. There tended to be a typical size of empire that for about 1,000 years, empires came and went, but their size was within a certain narrow band. And then there was a sudden jump, and suddenly empires were now much larger in size. So again, they were different empires coming and going, but they all tended to be of a larger size. And then that lasted for 1,000 years, and then there was a jump again, and now empires tended to fluctuate around an even larger size. So that's a little bit reminiscent of what's going on here. There's a fixed point here that it can sort of oscillate around, and then it goes round to a larger angle. None of these are stable, or none of these are fixed points, but when we get round to here, there's another attracting fixed point that it will tend to fall into. So that could be our next level up of empire. And we also see that same kind of quantum jump in the world urbanization fraction. Again, that didn't increase smoothly, but there were sudden jumps in the number of, or the fraction of the world's population living in cities. So this is why we're going to study this. If we can understand the dynamics of this, then it may be a model that we can use to think about and apply to similar situations that we find in history and society, where there's a quantization, there's a set of attracting points for something like the sizes of empires or the world's urbanization fraction. So let's have a look at then the dynamics of this using our phase space idea. And what we're going to do is really just put into pictorial fashion the things that I've been saying. So I've kind of really already covered the dynamics of this, but we're just going to put that down as a phase space portrait. So let's begin by thinking about the mathematical equation that describes this pendulum. Okay, so here's a diagram of the situation with the pendulum. So this is the pendulum, the rod, and it's at an angle theta to the vertical here. And it's being pulled by the acceleration due to gravity, g. And this acceleration due to gravity has two components. One component is perpendicular to the rod, so that's what's tending to pull the rod around. And the other component is parallel to the rod, so that's just tending to, stretch the rod or pull on the rod. So if we look here, that if we call this the angle theta is 0 when it's vertically downwards, at this point theta is 0, so sine theta is 0. So all of the acceleration due to gravity is parallel to the rod, just pulling the rod down. Because sine theta is 0, there's no component to the acceleration due to gravity pulling it in the direction perpendicular to the rod. So there's nothing pushing it, causing it to, or pulling it, causing it to turn. But if we then move it to a certain angle here, then some of the acceleration due to gravity is pulling it back in this direction. And the further we get away from the vertical, the bigger the angle. As we get up to an angle of 90 degrees, at this point, all of the force of gravity is still acting downwards, is perpendicular to the rod. So it's definitely pulling on it to cause it to swing round. But as we go back towards the vertical, the part of the gravity that's causing it to swing is decreasing. Most of it is, pulling along the length of the rod until we get to there when, as we said, it's all along the length of the rod and there's nothing pulling it one way or the other. But because it's swinging, it's got some momentum that will carry it through. Then on the other side, the acceleration due to gravity is pulling it back again towards the centre, and the amount of the acceleration is proportional to sine theta. So we can write the equation that describes the motion of the pendulum as that the acceleration of the angle is proportional to sine theta. It's related to g sine theta. So we can say that theta double dot is proportional to sine theta. Only it's not sine theta, but minus sine theta, because as theta goes that way, the acceleration is pulling it back this way. So we've got theta double dot is proportional to minus the sine of theta. Now, if we want to look at the phase portrait of this system, we can't do it just with this because this is a double dot. And as we said, for a phase portrait, you need only first derivatives. So we do the same trick I mentioned before when I talked about the simple harmonic oscillator. If we've got x double dot proportional to minus x, we replace, we write x dot as v in that case for the speed, and then v dot is proportional to minus x. Well, we do the same here. Theta double dot, we can write for theta dot as omega, Greek letter omega, the angular velocity, how fast the angle is changing. And then this equation, theta double dot, well, that's theta double dot is omega dot. Omega dot is proportional to, I'll just put equals, there will be some constant, but we could possibly choose the unit so that it makes the constant equal to 1. So I'll put it equal to, and we're only interested in the qualitative behavior of this system, not the quantitative behavior. So we can write omega dot equals minus the sine of theta. And that gives us a two-dimensional phase space. We've got 2 dimensions, 2 variables, omega and theta. And so we can now plot the phase portrait of this system with omega and theta axes. So let's have a go at that. Okay, so I've drawn the axes for our phase space. There's the theta axis and there's the omega axis. And I've also put in our fixed points that we already know about. So there's one when theta is 0. Then there's this unstable one when theta equals pi. And then there's another one at 2 pi, another at 3 pi, 4 pi, and so on. So we've got those in there, and the same for minus pi, minus 2 pi, and so on, if we go around the other way. Now, to fill in the what this phase portrait looks like, we could go from the equations, but it's kind of easier to do it just intuitively, just by looking at the pendulum. So let's consider if we've got this fixed point here, theta is 0. What happens if we start a little way away from 0? So, you know, if we're here somewhere, what's going to happen? Well, we're going to just oscillate, as you know, we know how pendulums work. If I move this away there, it will just oscillate back and forth around the 0. And omega will change so that at this end of the swing, omega is 0. And then as it swings back towards the center, omega increases to become maximum when theta is 0. And then it goes beyond it, or at least maximum in magnitude. And then it goes beyond it and slows down again, and omega is 0 at the other end of the swing, and then it increases again. Now, I mentioned magnitude because when theta is over there, omega is actually negative because it's pulling theta back to the center. So omega is going to move in the negative direction. So over there, that's at this point, omega is negative and theta is decreasing towards 0. So it will be going in the negative direction in the omega direction, and it will be coming back towards theta is 0. And then as it goes through 0, now omega is becoming less negative. Omega is moving back towards 0 as it comes towards the end of its swing, when it will stop momentarily. So theta is still well, theta's at 0, theta is still decreasing, it's now going into the negative angle, and omega, as I've just said, is coming back towards 0. And then once it reaches the end of its swing, omega starts to become positive, it's now moving back towards 0, and theta is also moving towards 0. So omega is positive and omega is increasing towards its maximum when theta is 0. So it's going to come up here. Omega reaches its maximum, theta comes back to 0, and then it goes on the other side of the swing. Omega is still positive, carrying it to positive angle, but it is decreasing towards 0. So theta is still increasing, omega is decreasing back towards 0. So in other words, we're getting a cycle around this fixed point. And that's when theta is 0. And now if we go all the way around to 2 pi, exactly the same applies. So we can fill in the phase portrait around 2 pi, 4 pi, all the even values of pi. There will be this cycle. And the same on the negative side. Okay, now let's think about what happens at these other fixed points, the repelling fixed points, which I slipped into the language, but it's worth mentioning. We can also call that an unstable fixed point, and then this is a stable fixed point. So an attracting fixed point is stable and a repelling fixed point is unstable. So let's think about what happens then if we start off at this angle pi, and we just displace it slightly. So it's very, very close to pi. What's going to happen? Well, it's going to swing round. Omega is going to be increasingly negative because it's swinging around this way. So the theta is measured in that direction, so omega is in the opposite direction. It's moving in this way back to through the center. So at this point omega will be at its maximum negative value, and then as we've gone past the center it will start to decrease again, and its momentum will carry it round just to the top, and then there it will stop. As it's losing momentum all the way around, it will just get back to the top, which is where it has the same energy. So drawing that on this diagram, what we're seeing is then that the angle will be decreasing, omega is negative, and it goes round here and it ends up at 180 degrees minus or pi in the opposite direction. And what could then happen from here is that it comes back this way, which would just be the opposite. Now omega is positive and theta is increasing. So it will go round, reaching its maximum at the top of the swing. And we can draw the same for all the other odd points, odd fixed points. And so I filled in the same picture for all the other repelling fixed points, all the other odd multiples of pi. There's a path from one repelling fixed point to the next and back again. And now let's think about what happens if we start off with omega outside this. So if omega and theta is inside one of these, we're going to rotate around that fixed point. We're just going to, oscillate around it. If we have got it all the way up to here, then that's the kind of the maximum swing that we can get back and forth. But what happens if omega is even larger? So let's say it's moving so fast around here that it goes all the way round, speeding up and then slowing down, but when it gets back to the top it will be going as fast as it was before, so it will carry on through the top and just keep swinging round and round. So that's like if you've given it a massive knock and it's just going to be swinging round and round like so. And how we would draw that on this phase portrait then is omega is so large here that it doesn't get back to 0 as it gets to the top, it just goes, and then it speeds up again as it swings back round to here 2 pi, which is back round to the middle hanging down position, but it doesn't get back to 0, and so it just does something like this. Okay, so my wavy line's got a bit wonky there, but you can see it's just oscillating up and down. And the same on the other side. This is if it's whacked in the opposite direction and swings round the other way. So the point to note here then is that with this pendulum system, with these equations, we get a phase portrait like that, and it produces these quantized fixed points where the system will tend to oscillate around. Now, I said that you know, if it's given a great whack, it will just keep oscillating forever like that. But that's not taking into account friction. So what will happen with friction is that in fact it might be moving fast here, but as it goes round, by the time it gets back to here, it's lost a bit of its momentum, lost a bit of its speed, so it won't be going a bit slower, and then the next time it comes round it'll be slower still, and eventually it will have lost so much momentum due to friction that it won't actually reach it, and then it will start to go into oscillations. So what could happen is we could be oscillating around this point. The system is given a whack, and it then follows the trajectory more like this into this part of the diagram, but because it's losing friction, it's coming back into here, and then it's kind of captured by this other fixed point. So we have these fixed points that represent successive levels of some variable, and a disturbance can knock it from one center to the next. And so this is a possible mental picture for things like the quantization of the sizes of empires. Now, actually, I'm not sure whether that is a good description of the quantization of the sizes of empires, but it's nevertheless a powerful model that we might certainly use in, if not in that situation, in other ones that we might encounter in socio-historical processes. But now you still might say, well, yes, but how are we going to get equations like this in socio-historical processes? Theta dot equals omega, okay, that's fair enough. It's just saying that's one thing, one variable depends on another. Let me just change this just to make sure we're not, you know, if we're applying this to socio-historical processes, we're not necessarily talk about angles, or we won't be talking about angles. So let's just emphasize that by, let's saying, instead of omega, we'll write y dot equals minus the sine of x, and then x dot equals y. So if this is, you know, x represents the size of empires that we're saying is quantized into different possible values along the x-axis here, that empires will tend to oscillate around, we'd have equations like this. But how are we going to get that something or other depends upon the sign of the size of the empire? It doesn't seem very likely in socio-historical processes. We can see how the geometry of the pendulum gives a sign, but how are we going to get that in socio-historical processes? Well, what we know, in fact, though, is that if y dot equals sine x, that would come from something like that. d2 y dot by dx squared equals minus y dot, because if we just recall that something like y double dot is proportional to minus y. That is the equation for a simple harmonic oscillator, and the solution to that then would be y proportional to sine of t, because this is differentiating with respect to time t. d2y by dt squared is proportional to minus y. So y would be proportional to proportional to the sine of t. But that's because we're differentiating with respect to time, so y is proportional to sine of t. But here it's d2 y dot by dx squared, and so it that should be minus y dot as well. Sorry. So instead of y, we've got y dot, and we're doing instead of differentiating twice with respect to time, we're differentiating twice with respect to x. But we've got the same basic principle that the second derivative is proportional to minus the value of the variable. So this will give, if this gives us y is proportional to sine t, in this case we've got not y but y dot is what we're differentiating, and it's going to be proportional to, let's put that there, that implies y is proportional to sine of t. Here it's going to be, because we're differentiating with respect to x squared, it's y dot's going to be proportional to the sine of x. So we can see then how we could actually get an equation involving a sine in a socio-historical system, because we're not introducing sine here, but sine is nevertheless a solution to that equation. So we're just saying that the second rate of change of this variable is equal to the minus the value of the variable. And I've called it y dot, but you know, y dot could be z. And then we'd have our system of equations, d2z by dx squared equals minus z, y dot equals z, or proportional to z, and x dot proportional to y. Those three equations would result in y dot equals minus sine x and x dot equals y, which would then give us this phase portrait. So if we think that this phase portrait describes the socio-historical system process that we're looking at, then we can start to look for variables x, y and z that are related in that manner, and then it will generate this kind of phase portrait. So that is why we're interested in it. Okay, so I've just given you a model that may or may not be useful when we're thinking about what kind of mathematical equations would describe scenarios that we could come across in socio-historical processes. And that is why this module is called Mathematical Methods for Theoretical Historians. It's building up a toolkit of mathematical ideas that we can bring to bear on the problems of socio-historical processes. And it's not just about particular models, but it's also about techniques. So this technique of the phase space portrait can be a very useful way of analysing our data and help us bring out some of the patterns in the data. So if we have a time series, let's say at time t, we've got a set of times here, 0, 1, 2, whatever it might be. And we've got a set of values for x, you know, 3 and whatever. So we've got a time series saying how a certain quantity x, which might be world urbanization fraction, or the amount of war in the world system measured in fatalities per year or something like that. We've got something telling us how that is varying over time. Then we can plot a phase portrait of x dot against x. Now we haven't got x dot here, we've got xt, but x dot is just the rate of change of xt, so it's xt plus delta t, the value of t at time t plus delta t, minus the value of x at time t, divided by the time difference. So that's the amount of change in x in time delta t per time delta t. So that's a rate of change of x, and is therefore x dot. So and we can get all that from this, this table. We've got all the xt's. We know what the delta t's are here. They may not be the same. We might have different delta t's, but we still just can apply that. And so we'll get some values for the x dot, the rate of change, and then we can plot a phase space graph. And if we're lucky enough that the data comes with a constant delta t, let's just write this up here actually. This is going to be, this x dot is going to be xt plus delta t minus x of t over delta t, that's x dot. So I was saying, if we're lucky enough that delta t is constant throughout this, then delta t here is just a constant. So it just affects the scale on this axis. So we actually don't need to bother with the delta t. So we can get rid of that, just ignore that. The pattern will be the same. So in other words, we can just plot x of t plus delta t minus x of t against xt. So in other words, we plot the difference between successive values against the value. And we might get, something like that, a phase portrait, or perhaps a bit of a happier example, we might get something like that. And we'll say, oh yes, okay, we've got a cycle. Or, we might find something spiraling in towards that, and we say, this system has a limit cycle that we're moving into, something like that. So the basic point is a useful technique. Just plot the difference of successive values against each value. So xt against the next value of x minus xt. Or if they're not equal time intervals, you need to divide by delta t for each one. And in fact, another thing we can do is just plot x of t plus delta t against xt. And for known equations, there will be known patterns how this would look. So for example, for a logistic curve, or rather the time derivative of a logistic that goes like that. So let's say, just to give a concrete example, this is cases per day in the pandemic, that's time t days. So for something like that, if we plot x of t plus delta t against xt, we get a sort of lobe, something like that. That's where they're equal. So initially, the value here, then the value the next day, cases per day, is greater than it was the previous day. So it's going outwards, and it's above the line where x equals y, or when xt plus delta d equals xt, the 45-degree slope. It's going to be above that because the cases are increasing. The cases the next day are larger than they were the previous day. But then when we get to the maximum here, it turns around, and now the cases per day are always less than the cases the previous day. So it lies below the line of equality here, and it comes back. So, and also the cases per day start off very small, and they become large and then they become small again. So if we just plot the cases of day n against the cases for day n minus 1, and if it's a logistic growth, we should get something like that. And in fact, if you did plot the cases per day in this way, so the cases of today against the cases yesterday for the pandemic, you got something that sort of went all over the place, but did look something like that. So if you've got something like that, you would say, well, it's kind of logistic, but it's not really a very good logistic. But it's gives you a visual representation of how well it fits a logistic. So perhaps I'll just summarize. Some things we can do in data analysis is xt plus delta t minus xt over delta t versus xt, or just xt plus delta t minus xt versus xt if delta t constant, and then lastly xt plus delta t v xt. So plot the next value against the previous one, and those may give you pictures that help you think about what's going on.